All right, welcome, ladies and gentlemen, to the first section for Chapter 4. We're going to be looking at rational functions and asymptotes. So we're going to look a little bit at domain as well, but really jumping into the idea of an asymptote. So first of all, let's define what a rational function is. A rational function is just a function that can be written in the form f of x is equal to n of x over d of x, where n of x and d of x are just both polynomials. That would be something along the lines of 3x squared minus 4x over 2x minus 1. This would be a rational function because the numerator and the denominator are both polynomials. We also have to make the statement that d of x cannot be 0, and that's actually going to play a big role in this stuff later. And the domain of f of x is all real numbers except for the x values that make the denominator 0. So we're going to start off with, let's see if I can find there it is. We're going to start off with the function f of x is equal to 1 over x, just to kind of show you what these functions kind of do. And we're going to start off saying that the domain is everything except for 0. That's what this represents, negative infinity to 0 and 0 to infinity. Because this is 1 over x, 0 is the only thing that makes this 0 in the denominator. And what we're going to do is we're going to sketch this graph just to get an idea of what these types of functions do. And we're just going to start by using a table. So if I started with the positive values, we could say, oh, let's start at positive 10. If x is 10, this becomes 1 over 10, which is 0.1. If x is 5, then I get 1 over 5, which is 0.2. If I just start choosing some values here as I get going, actually let's start with a 2. Let's get 1/2. Go to 1, it's 1. If I plug in a 1/2, here's where you might have to think a little bit harder here. If this was 1/2, it would be 1 over 1/2, which is 2. So this becomes a 2. If I go to 1/4, this becomes 4 in the same fashion. 1/5 becomes 5 and all that sort of stuff. So if I looked at using the numbers out here, 1, 2, 3, 4, and 5, and I go 1, 2, 3, 4, and 5. Now, if I plug in an x equals 5, I got 0.2. So that's like right in here. I plugged in the 0.2, I get 1/2, which is like right in here. Plug in the 0.1, I get 1. And kept going in, and I got a 2, and then a 4, and then blah, 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 I get farther up. So notice that these points kind of follow these two axes here. And I can kind of come down and draw this graph that looks like this. Now, what this does is it doesn't cross the y-axis and it doesn't cross the x-axis. As x keeps getting bigger and bigger and bigger, this fraction keeps getting smaller and smaller and smaller. And likewise, as x gets closer to 0, y gets really, really big. Well, the same thing happens if I was to make these negative values. It just makes these negative values. So I get both negatives, and it follows the same pattern on this side. So you'll notice that this has a vertical asymptote at x equals 0, and it has a horizontal asymptote at y equals 0. All right. Now this is just stuff, this is kind of a basic idea of what these graphs are going to look like. Not all of them look like that. Some of these have more than one vertical asymptote, but that comes up in a little bit. But this is the basic. This is kind of our parent function, the 1 over x. All right. If we were to move forward and look at vertical and horizontal asymptotes. A vertical asymptote is always the equation x equals a number. It's a vertical asymptote if we say it approaches infinity or negative infinity as we approach that x value. So, if we're talking about a vertical asymptote over here at a, if my function goes to infinity or to negative infinity, or both in this particular case, then that's called a vertical asymptote. They are relatively easy to find. I'll get to the horizontal. Actually, I guess I got to talk about horizontal first. Let me talk about horizontal. Horizontal is a horizontal line that as x gets really, really big or really, really small, it approaches that value. So if we talked about a horizontal asymptote right here, should be a dashed line, and we went like this, as x gets really, really big, the y value gets really, really close to the asymptote, and the same thing out here. We're talking about way out here. You can cross a horizontal asymptote, but the idea of that is if I had a horizontal asymptote like this, if my function did all sorts of stuff out here and it crossed the asymptote, the idea of a horizontal asymptote is that it must come back to the asymptote and follow that dashed line. This is more of an end behavior than it is a thing you cannot cross. You cannot cross verticals, but you can cross a horizontal. So now let's talk about what I wanted to talk about, how to find asymptotes. Vertical asymptotes occur wherever the denominator is 0. So we're looking at x equals some number. So we've been dealing with this quite a bit already in our last chapter, dealing with finding zeros of a polynomial. So that's what we're going to be doing now. So if I had something like 1 over x minus 2, that means I have a vertical asymptote at x equals 2 because it makes the denominator 0. All right, horizontal asymptotes are a little bit more challenging. Horizontal asymptotes require you to look at the degree of the numerator and denominator. If the degree of the numerator is less than the degree of the denominator, then y equals 0 is an automatic horizontal asymptote. So if I had 1 over x plus 1, the degree up here, right, this is x to the 0 power, and this is x to the first. So the degree is 0 over 1, so therefore y equals 0 is a horizontal asymptote. If they are equal, if your degrees are equal, let's say I had 2x squared minus 3x plus 1 over 6x squared minus 2x minus 7. If the degrees are equal, which they are because I have squares, then it's the ratio of leading coefficients. So my horizontal asymptote in this case would be y equals 2 over 6, which is 1 over 3. And lastly, if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. Now, there is something called a slant asymptote, but that comes later in this chapter. So right now, for horizontal, you're either going to get 0, a ratio of leading coefficients, or none. So let's try to do a few examples here. We're going to look at everything on these particular examples. Oops. Let's try something here. Let's try 2x over 3x squared plus 1. If I wanted to think about the domain, I need to think about what makes the denominator 0. Well, I got to set it equal to 0, subtract 1. I get x squared equals negative 1/3. Well, that means, or sorry, 1/3. I can't square root negative numbers, so that means the domain is all real numbers. And if the domain is all real numbers, there is no vertical asymptotes. But what about horizontals? If I look here, this is 2x to the first power over 3x squared. The denominator has a higher degree than the numerator, and therefore it's y equals 0. If I was to do kind of a same type of example, and let's make both of those squares. That's supposed to be a 1. All right, so again, the domain is all real numbers because the denominator is the same, which means I don't have any vertical asymptotes. And my horizontal asymptote in this case is they have even degrees, or they have the same degrees of 2, so it's y equals 2 over 3. All right, what else can we do here? Let's try something else. Let's try something along the lines of 4x minus 1 over 2x squared plus 3x plus 1. And I want to find the asymptotes, but I also want to find the domain in this case. So I need to look to see when does the denominator equal to 0. And what I do straight away is I just factor these problems. So this becomes 2x plus 1 and x plus 1. If you refoil this together, you'll notice that I get this. So my domain is everything except for negative 1 and negative half. So it's negative infinity up until negative 1, negative 1 to negative half, and negative half to infinity. So that's my domain, and that actually goes hand in hand with my vertical asymptotes. My vertical asymptote is anything that makes the denominator 0. So it's this case x equals negative 1 and x equals negative 1 half. And then my horizontal asymptotes. Horizontal asymptote in this case, this is a first degree polynomial over a second degree. So the denominator is bigger, and therefore y equals 0 is our horizontal asymptote. Now, if we were to try to graph some of this stuff, which we will do later, if I was here at negative 1, I would have a vertical asymptote at negative 1, I would have a vertical asymptote at negative half, and I'd have a horizontal asymptote at 0. And then there's graphing that goes on inside of this. And it could be all sorts of different things. It could have little things in between these two dashes and a little thing on the outside, a little thing on the outside this way. One thing that I want to mention that I forgot to mention a second ago or towards the beginning was something like this. We know the graph to look like this. When we're dealing with very basic graphs like something like this, if you remember transformations, to go from this to this is a right 5 translation. And that should actually make sense because my vertical asymptote is 5, or x equals 5. So my vertical asymptote goes from my parent function of x equals 0 over to x equals 5 and follows the same pattern. Right? So if I was to do 1 over x minus 5 plus 3, this would move my vertical asymptote over to 5 and my horizontal asymptote up 3 units, but still it would follow the same pattern. This will help you do a little bit of a matching a graph with an equation. So if you remember some of your transformation rules. But if you think about the fact that this is x minus 5 says a vertical asymptote at 5, it really does make it look like it's translated to the right 5 units. All right, so finding asymptotes is really important for us, so I hope you learned something about that in this lesson. I will see you guys tomorrow.